Oh, good. Let's get started. Thank you. Thank you very much. I love when you guys are chatting. The other section's a little quieter. You guys are always nice and chatty. So we're done with particle in the box, and sort of. It's always gonna come back to haunt us. In certain ways. But what I want to spend today. So I forgot. I wanted to ask you all to bring your slinkies, and I don't know if you did or not. Bring them next week. And the reason why we don't need it right now. I'm sorry, you're up chairs. Where the hell did everything go?
In my back pocket. I don't know.
It seems like the box is open.
Yeah. Okay. You can sit at my table if you want.
Oh no, I don't want to be.
What? If I didn't bring my bring I want to take Angela can't see it.
Okay, I'm used to it.
I want to take another break, a short break, not really a break. This is useful information. This is actually to give you a lecture that I give much later in the semester. Partially, I'm going to kind of take and pull from it. What I want to do is I want to place the particle in the box in the greater chemical contents. All right, I want to kind of think about why we spend all this time on this and why it matters. And through that contextualization, we're going to come up with a set of goals that we can identify about the rest of the semester. We're going to kind of set up the rest of our class here by thinking about molecules. So I want to put particle in the box in the context of molecule. You're probably on the homework right now. You're looking at a nice example of where the particle in the box approximation can be helpful in interpreting molecular information. And you'll see a lab in the third rotation this semester that explores it as well. I want to think about particle in the box in a different, more abstract way when it comes to molecules. And what does it represent? Where is it a really good model for molecules? Well, you see in the homework, it's kind of a nice approximation, but it doesn't work all that well. Where does it work really well? And what we should first think about are the lessons that we learned in the box. And I think the best way to think about particle in the box is to, for one last time, draw a box. And I think this might be my first three-dimensional box in the class this semester. There are some people in this room who've never seen me draw a 3D box, and some of you are sick and tired of it, I'm sure. And some of you have gotten really good at it over the last year. Big box, right? We can label it X, Y, and Z. Right, and instead of putting an electron in the box, we put a molecule in the box. All right, we got this massive molecule HCl. Right, we can think about the particle in the box representation as the molecule just moving around in a box of some size. So it's got some wave function, which has, as you guys probably, if you haven't started the work, has 3 quantum numbers, one for each direction. And it's a function of X, Y, and Z. Right. And what do we know? What did we learn about this wave function? Well, it's wave-like. Right. Along one of the directions, it looks like a sine wave. Right. Looks like a sine wave. We saw that. The more interesting thing is that the energies, the allowed energies of the system are quantized, which means that they're numbered. Right? And we saw that the energies of this system are proportional to h squared, n squared. Right? And n can be an integer. And this is, oh, sorry, n can't be 0, sorry. And this is a unique property of a quantum mechanical system that has quantized energies that is distinctly different than a classical object. classical object can take any value for its energy, meaning that its energy space is the real numbers. You can label each energy of a billiard ball with a real number, so infinity real numbers. In a quantum mechanical system, you can only label the energies with integers. And the size of the integers is explicitly a smaller infinity than the size of the real numbers. I know that's a weird concept. They're both infinite. You can prove that the integers are a smaller size of infinity. It's a smaller infinity than the real numbers. And so by definition, the allowed energies of a quantum mechanical particle is inherently less, infinitely less dense than the density or the energy levels allowed for a classical billiard ball. So infinitely more sparse. Right? That's very, very unique and very powerful. And we showed in class last time that this enables spectroscopy. These two combinations of things that give us spectroscopy. A slightly more subtle thing, which is that the wave function is intimately related to the boundary of the space that it exists in. Right, we saw that when we looked at the free particle, and then when we put it in a box, you got discrete energy levels. That the only thing we did was we applied a box. So the system responds to the environment, right? Intimately. The entire representation of our particle changes when we go from a giant room to a very small box. Right? It's quantized energy levels. You get wave-like behavior. And we're going to constantly think about this idea. This third one is so important. The idea is that psi of x is not, in some sense, for every system that contains an electron, they all have the same kinetic energy. But the potential energy varies on the system, right? Whether it's a box or it's an empty room, or it's a hydrogen atom, or as we'll see a bond, you get a different boundary for that wave. And the behavior of that wave is directly related to that boundary, right? So this idea of boundary conditions is essential, right? And the way that we define boundaries defined using potential energy, right? That's what the potential energy in some sense is used for in these problems. So we think about the potential energy as a way to define where the space of motion can be. And we saw that in the particle in the box for energy. What we might want to think, right, that's the particle in the box is the simplest idea, right? Where the potential energy is infinite outside the box and the box is zero. That's the simplest thing that we can come up with. What if, for instance, that boundary is somewhat squishy, right? You can press against it. Right, that you can push against the walls, and that the boundary can extend and extend and extend the harder you push. That's an interesting thing, right? Where you have something that's confined, but only confined by as much as you can pull it apart. Right there, the boundary changes as a function of the position. That's a different thing about. Right? Maybe the waves look differently there. What I really want to get at, though, is that what this model really tells us, if we can use it for different things, right? By changing what's inside the box and the shape of the box, we can model different things. But what this really is the theory of molecules moving, X, Y, and Z. That's all it is. It's just the theory of how molecules move in a space or any particle, right? So we say that the particle in the box is a theory of what we call translation. Right, the idea that it tells you something, right, that psi squared gives you some information about the probability that something at x0 ends up at some other position, x final. It just gives you some trajectory. Well, it doesn't give you trajectories, right? It just gives you probability that where to find the particle. That's all it tells you. right? So, but it's a theory of translation. It tells you, in some sense, what you observe when you observe the molecule moving in space. Nothing is happening to the molecule itself. It's just a ball of some mass. But its motion is quantized in this way in the box. And you're looking at the data in the homework. Right? So I like to think of translation as XYZ motion. Right? Certainly we can think about it in time as well. But let's just think of it as XYZ. Okay, so that's like, what we should think about instead is now we're done with this particle box. It's not the last time I'm going to bring it up, but for now we're going to walk away from it for a little bit. And ask the question, if this is the theory of translation of a molecule, what are the other motions that a molecule can do? This is like one of the things the molecule can do. I can move X, Y, or Z. What are the other things the molecule? So what I want to think about today is molecular motion. The motion of atoms and electrons together or separately. We know that there's some internal structure there, right? We've got a bond between the H and the Cl. The H has a proton and electron. The Cl has a bunch of protons and neutrons and electrons. It has tons of them. Right? You've got all these little particles moving around. But if we want to think, for instance, about how this molecule moves in space, do we really need to think about how the electrons are moving? No, not really. So we need to ask that. That's the important question. What simplifications can we make, right? Can we just, when we think about X, Y, and Z motion of a molecule, can we just really blur out what's actually happening inside? It should be obvious that's probably the case, right? And you guys can recognize this from the ideal gas law. The ideal gas law is the consequence. All ideal gases, regardless of their characteristic, what molecule they are, what atom they are, all interact and move exactly the same way. So the ideal gas law is proof positive that the internal characteristics of the molecule are completely negligible. Right? So this is a universal theory. This is a molecule agnostic, which means it doesn't care, theory. Okay. Only cares about the mass. Right? And the proof of this is the ideal gas law, which is just the theory of motion of a gas, of molecules at thermal equilibrium. Right? That's all Pivner is, right? We saw that last time. Right? That's just the ideal gas law. And it's very easy to go from this three-dimensional particle in the box with a little bit of thermo and get the ideal gas law. Right? They're directly connected to each other. All right, so there's proof that we know that the ideal gas law isn't 100% true. It becomes less true and the molecule starts to matter, but that's not here nor there. As we saw with van der Waals, it didn't really matter what was going on in the molecule. Each molecule was slightly different. We gave it two little numbers, A and B, to distinguish it from other molecules. So we just think about them in very average ways. Right? We don't think about how the electrons are shared between the H and the Cl, for instance. We don't care about the electronegativity, really, when we think about motion. But obviously, there are contexts where that matters. Certainly, if we think about the molecule by itself, its structure really matters. So let's think about the other types of motions that a molecule can undergo. Right, so maybe it's worth thinking very abstractly about what a molecule looks like from a physical chemist point of view. We should think about all the little things that are moving around. All right, so let's just do a quick example. And let's just think about H2. Right, let's think about the coordinates of hydrogen. This is something that I usually give far later, right? But I think we can intuitively understand this without having to do any math. Okay? We can come back to it later when we do have it. Let's think about what hydrogen has, right? Hydrogen has, we're going to assume that they're regular hydrogen atoms. So each hydrogen brings a proton and an electron to the table, right? they have masses. It might be worth thinking about what the mass difference between the proton and the electron is. It might be worth, I'll just write that over here on the side. The mass of the proton divided by the mass of the electron is about 1800. The proton is almost 2000 times heavier than the electron. Right? So we have these two massive objects, and we have these two really tiny electrons. Actually, they have no size, and they have much less mass, just buzzing around. Okay, so let's set that up. Let's set up a little coordinate system. So here's proton 1. Let me get my notes really quickly so I don't screw this up. Perfect. All right, we'll call that atom A. Okay, and then there's proton 2. Call that atom B. Right, and we'll separate them at some distance, right? There's a bond length in H2. I don't know what it is, but we'll just make it a variable. So we'll separate them by distance r. Okay, and we got 2 electrons. I don't know where they are, but we can just draw them somewhere. We have E2. And over here we have E1. It could be anywhere. You know, they could be on both sides. They're shared across the bond, but we can draw little vectors pointing to them from all the different atoms, different directions. So let's draw some vectors, just kind of define our coordinates. We have a vector that points to A to the electron 1. We'll call that R1A. We have R2B. We also have the cross ones. R1. So that's R2A. And we have the other cross one. R1B. And then there's a coordinate between the 2 electrons, the relative coordinate. Call that R12. Okay. So that's a reasonable way for us to define the coordinates. We think about what is going on in this system, right? What do we have? We have some positive charges and we have some negative charges. We know what those do to each other. So the forces, what are the forces acting on this system? Well, there's only one force. There's the electromagnetic force, Coulomb force, right? The electrostatic force. Right, which we call the Coulomb force. Right, between E and P. Right, and we know the rules. Right, we know that the force for electrostatic is attractive if between E minus and P plus, right? Positives and negatives, opposites attract. And it's repulsive if between likes. Okay. We can write down a formula for what that force looks like and the potential energy. We're not going to do that. We'll do that later. But we can just think about this schematically. Right, let's go back to how we set up the particle in the box. Particle in the box is we set up the Schrodinger equation, which was that energy equation where we solve for the wave function. And the thing that we did was we wrote down the kinetic energy and the potential energy of everything in the box. Right? In the box, there was only one object, just the electron. So we had one kinetic energy term for the electron, and then we added the potential of the box. Now here we have lots of different kinetic energy for objects. We also have lots of different forces. Right? Everything is either retracting or repelling each other. Right, so we should write down what's the total energy of the system, right? That's the goal, right? We're trying to find states of constant energy, wave functions. And so we should write down what are all the different energies and all the different interactions occurring. Right, so we define what's called the Hamiltonian, right? The H operator for H2, right? That's the total energy. Right, and it's going to be the sum over all the particles of their kinetic energies, right? T sub I. And then we're going to sum over all the pairs of particles, their interactions, their forces, right? Because those are defined between pairs, right? So we define the potential energies between two of the different particles. Okay, so these are the kinetic energies. And these are the potentials. Right? Now here's a nice formula you guys might have learned in physics 1 and then proceeded to forget. How do you get from forces to potential? Just a derivative. This is from Newton's second law. Let me just make a note here on the side that the force is equal to the minus the derivative of the potential with respect to position. Okay, so if we know the forces, we just have to integrate it to get the potential energy. Or if we know the potential energy, the force is the derivative. We'll come back to that. That'll be important when we start talking about Bob. Okay, so we know what the forces look like. We can write down an equation for it so we can get a potential energy. All right, we'll do that when we start solving this problem properly. All right, so we're summing over the kinetic and the potential, and all I have to do is just look, right? I just have to look and I say, okay, I've got all these interactions, they all have coordinates. So I can just write down little terms that represent each one. So I have the kinetic energy of E1, right? That's a function of the position of it relative to A. So that's a function of R1A. I have the kinetic energy of E2. That's a function of R2B, right? We're just going to say that electron 2 is being, the idea is that electron 1 comes from atom A and electron 2 comes from atom B. They're connected to each other. So I just represent them that way. I could write it any way I want because they're all shared. I think that's a convenient chemical way to think about it, that two atoms are bringing in electrons to share, and they initially are connected to each other. And then we have the kinetic energy of the nuclei. Okay. Those are our kinetic energies, right? There's 4 of them because there's just 4 particles. And then I have all these odd potentials, right? I have all these connections, right? So there are, let's kind of write down all the different connections we have. We have 2 repulsive connections. We have 2 repulsive interactions. The 2 protons repel each other, and the 2 electrons repel each other. And all the other ones are attracted. So both electrons are attracted to both protons and vice versa. So we've got a bunch of terms here. So we have the potential of attraction between 1 and A, the potential of attraction between 1 and B, the potential of attraction between 2 and A, and the potential attraction between 2 and B, right? Those are the attractions between the nuclei and the electrons. I'll write that here. And then we have these 2 repulsive terms. We have VAB, and we have V12, right? Electron-electron repulsion. And this is nuclear repulsion. Okay, so I can write down formula for all of these. Right? I can write down equations for each one. Right? We'll do that. Solving it is a different question. But I hope that the kind of philosophy or the goal, the mechanism I'm trying to do here makes sense. I'm just adding things up and just tallying up all the energies in my system, and then taking all of this. I take all of this and I solve for the wave functions that satisfy the Schrodinger equation, the eigenvalue equation for this operator of all these energies. All right, it's already hard enough to do one operator. Now I've got 1, 2, 3, 4, 5, I got 10 of them. And this is just for hydrogen, right? Now I go to uranium oxide, and I've got 100 electrons. And tons of two nuclei, right? But they have lots of charges. Very, very complicated problem, right? So this is just the best case scenario. Right? So, and here's the biggest problem. Think about it, this wave function is a function of all the coordinates. Right? It depends on the wave function depends on the kinetic energies, it depends on how the electrons are situated relative to the nuclei, and how the nuclei are situated relative to each other as well. So you've got this soup of moving objects. Right? How do you even start to analyze? Right? What it kind of seems like to me, from our understanding, right? Remember that the wave function is sensitive to the boundary that we create, and the boundary is the potential. But the potential tells you where these particles can move. It is the boundary. They create their own boundary through their attractions and their repulsions. And we saw that the wave function is intimately sensitive to the boundary. So I've got this very, very chaotic boundary, right? The boundary changes based on where the nuclei are relative to the electrons and as well to each other. So this is an extremely complicated problem. Right? If we think about the wave function of the electron, it's a function of the positions of A and B, as well as the electron coordinates. Right? And the electrons for the nuclei, the wave function for the nuclei are a function of the nuclei, as well as the electrons as well. They all depend on each other. All right, so everything is moving around and fluxional. And God knows what this looks like. Right? It's a horribly complicated equation. Good luck getting to just a couple of sine waves how like before. So what can we do to make this easy? How can we simplify this problem? How do we even make progress? Something you might have an appreciation of already is we implicitly make an assumption when we do spectroscopy. What happens when you do spectroscopy? Well, you pick an energy of your light, and what does that light do? It probes some specific motion in the molecule. Microwaves and magnetic fields do NMR, infrared does vibrations, UV vis excites electrons, X-rays ionize electrons and break bonds, right? And I do microwaves. Microwaves rotate molecules. And what you find is that at each level, energy, you're exciting a different motion. And in some sense, the other motions don't matter as much. And when we do NMR, we don't ever think about electrons being excited. We don't really think about bonds vibrating. Sometimes you do, but most of the time you don't. Most of the time we think about molecules as rigid objects. But also when we're at really high energy, we're doing UV vis, you're not thinking about spins of nuclei or spins of protons like you are in NMR. So there's a disconnect in the motion. They're not all connected to each other. So that means implicitly that there must be some way to separate all of these things out. Right? We do it in spectroscopy. Spectroscopy takes advantage of the fact that things seem to be separable in molecules, and they are. This is actually the contribution of Robert Oppenheimer I find to be the most important, and the one they didn't study in the book because it's the least interesting, it's the least glamorous and destructive. But Robert Oppenheimer's PhD thesis, before he started the Manhattan Project and all that junk, his PhD thesis with Max Born was on this separation of the motions in molecules. It's called the Born-Oppenheimer Approximation. And I want to talk to you about the Born-Oppenheimer Approximation today. And it takes advantage of this, that the mass difference between the protons and the electrons is massive. Right? In fact, we really don't, from the point of view of the electrons, the protons don't look like they're moving at all. Right? And from the proton's point of view, the electrons are just buzzing around them in some average way. So Oppenheimer in his PhD thesis comes up with a way to characterize this. And I want to kind of explain it to you in a very like grade school kind of way. If you take spectroscopy from me, I'll teach you the whole thing. But I think it's easy to think about Born-Oppenheimer from a very intuitive way. Okay, so here's that observation I made, that MP over ME is 1800. Right, so let's think about the kinetic energies of these two objects. The kinetic energy of the electron is minus h bar squared over 2me times the second derivative with respect to space. And the proton has a very similar structure, h bar squared over 2 times the mass of the proton times its second displacement, respect to position. So when I take a ratio of the two.
Second.
Yeah.
There's a thing blocking.
Oh, I'm sorry.
It's okay.
Thank you. When I take a ratio of the two, right, they're linear in the mass. Right? So this ends up being proportional to equal to ME over MP, which is about 1 over 1800. Right? So what this says is that relative to the electron, nuclei move very little. Okay. Right. And this kind of then therefore says that, and the reason why is because then now the velocity of the electron on average, which isn't a well-defined concept, but if you think about kinetic energy as 1/2 mv squared, then, sorry, the velocity of the proton. Oh, nope, that's right, the electron, sorry. I can't do math. Is about the square root of the 1800 times the velocity of the proton. Right? So that means that basically the idea is that relative to the electron, the proton doesn't move at all. It's stationary. Okay, so what Born says, this is what's called the Born, and I'll say it in a second. So relative to nuclei, electrons move rapidly, which means basically is an equivalent statement as saying is that the nuclei are frozen, are effectively frozen. Okay. So the consequence of this, that Born and Oppenheimer come up with, it's really Oppenheimer who comes up with this. Born is just there to hang out with him mostly and give him advice. Is that nuclear coordinates and motion are independent of electronic motion, electronic coordinates. All right? So the nuclei basically act independently of the electrons. All right? This is called the Born-Oppenheimer Approximation. In the movie, Oppenheimer gets his PhD and he goes to visit Einstein at the Institute of Advanced Study in Princeton, the research institute that Princeton created for Einstein to get him out of Germany. That was how they got him to Princeton. So they created an entire institute for him and a place to live and teach and work. He comes to visit and Einstein has a conversation with him and says, "Oh, your PhD thesis was very good. I really liked it." And that's all they say about it. But Born-Oppenheimer approximation is the basis of spectroscopy. It's the reason why each type of spectroscopy gives you different information about a molecule. Because the things that the motion of nuclei is independent and different than the motion of electrons. Right? So there are types of what we call nuclear spectroscopy. They're not, we're going to be very careful about that concept, but the idea that spectroscopy excites nuclear motion versus ones that excite electronic motion. okay, where the electrons get excited. Two very different things, and they act independently of each other. Let me give you a very, as I said, first grade explanation of this. It's one that I'm quite fanciful of. I want you to think about the nuclei as an elephant. Now watch me draw a terrible elephant.
Oh.
All right, there's my elephant. Here's my nuclei. All right, there's my nuclei. It's this big fat elephant. All right, I need to copy them because I need to paste them later. And God forbid I'm going to draw another one of these stupid things. All right, come back to that. All right, and what I'm going to treat, right? So our nuclei are these. So the electrons are the little dirty flies that are flying around it. All right, you got all these little flies that are flying around. The nuclei. Okay, and we can track them, right? We can track them. We can track them by tracking their positions as a function of time and their momenta as a function of time, classically. I'll color code it, right? All right, and let's just kind of propagate them at the same time. I should call this X prime, P prime. Right, and the elephant is moving along, right? So the elephant is doing something. Maybe he's being poached or something. He's running. All right, something happens. I know that's a terrible. Okay, so he's running to get a nice picture for the TikTok. All right, so something happens to the elephant. I actually need to redraw him because I need to make him in motion. And I'll give him some like anime action things like this. He's running away. All right, and so what happens is the elephant suddenly changes position. Right, and what happens to the flies? The flies immediately reorganize themselves around the motion of the elephant, right? So now you've got, this fly right here is going to start buzzing out of the way. This one wants to grabs on here. Maybe this one sticks. I forgot his tail. There we go. Right, and this one, avoids contact, right? So the electrons quickly readjust. And relax to elephant's new position. Right? Their goal is to eat dirt and crap off the. Literally, they're just there to poop off the elephant, right? They're not really there for anything else, and so they're going to adjust to their food source very rapidly as he moves. Now, what happens if instead you introduce a flow of 100 ppm of DDT into the atmosphere, right, which kills flies, but 100 ppm, the elephant don't give two shits about 100 ppm. Right, so flies, so this is, so flies suddenly move, right? Right, and so the flies, of course, or now I need my elephant. Right, the elephant doesn't give two craps, but what do the flies do? Well, some of the flies die, right, and some of them, and they start leaving. They start moving around differently, right? The flies move on, and what's the elephant do? The elephant's completely uninterested, right? So the elephant just continues on. Elephant unaffected. Eventually, the elephant, over a long time, might realize that the flies are gone because he's accumulating a lot more poop on his back than he usually does, or something like that, or gets sick and dies from not having it properly removed through its symbiotic relationship of insects, right? But the results are long term, right? So elephant is unaffected short term, right? And then maybe later down the line, the elephant adjusts to the fact it doesn't have flies anymore, right? Eventually, the elephant stops flicking its ear and its nose, right? It starts to return back to and chew it. I don't know what elephants do. I was going to say chew its cud. I don't know if elephants chew cud, right? And slow relaxation for the elephant. Molecules work exactly the same way. Right? Molecules work exactly the same way. Right? Molecules work the same. I'll do this in a different color. Let's do green. Right? When electrons rapidly respond to changes in nuclear arrangement. I spell that out. It's arrangement. And nuclei slowly or don't even respond, if at all, respond to changes in electronic structure. Right? Same idea. Right? Open plus. Right? So the consequence of this is important. What we can do now is we can separate the nuclear coordinates from the electronic coordinates. The electrons move around nuclei that are frozen. So what we can do now, of course, the nuclei can move. We can stretch them, stretch the bonds, for instance, with vibrations. The idea is that at every point along that stretch, the electrons relax. Right? The electrons rapidly relax faster than. So Born and Oppenheimer come up with a new approximation to our hydrogen atom. Right? So what they do is what's called the clamped nuclei approximation. Right? And the idea is very simple. Right? The idea is that you fix R, the big R, right? That's the space between the nuclei. Right? You fix R, and you allow electrons to relax around stationary nuclei at distance R. Right, so what you get out of that, when you do that, you get a wave function for the electrons. That is a function of the electron coordinates, however many there are, but it's defined at a specific value of R. Okay, so what I do is I have a wave function for my electrons at every value of R. Okay, and I can get electronic energy out. Right, I can take the Hamiltonian that we defined earlier and apply it to this wave function. And what I get out is the electronic energy times the wave function, just like I did before. Right, but it's at a fixed value of R. All right, so this is what this fixing of the distance is called clamping. And we allow the electrons, we solve the electrons around those fixed nuclei. And then what we do in order to understand the full molecules, we just step the nuclei into it again. So then we just step R. Okay. So what do we get? Well, we can make a plot. So if we look at HCl, for instance, or any molecule, any diatomic. Right? There's only one bond length, right? There's only one R that we vary. So what we can do is make a little plot of R versus the electronic energy, the energies of the electrons in their ground state at that position R. I'm going to set 0 to be in the middle here, which we're going to define as the electrons are neither repelled or attracted to each other, that there's net zero attraction in the system, right? It's just like no repulsion or attraction between the electrons. At long distance, we know exactly what that looks like. If you put the two atoms at really far distance, there's no bond. The electrons don't interact. One electron's on A, one electron's on B, and none shall they combine. So at long distance, we know this energy kind of is like there, right? It's at 0 at long distance. At really close distance, that's where the nuclei are pushing against each other. And that's extremely repulsive. That's the last thing we want. So the energy skyrockets at at close distance. And we get a curve that kind of looks like this. Right? Like this. Right. And we find that there's this unique spot, right? This equilibrium distance. You guys probably remember this from last semester. This is just the Lennard-Jones potential, right? But it's the same idea. That there's some equilibrium bond distance that's the most stable form. So what is this function? Well, this is the energy of the system as a function of R. So this tells you, if you think about an electron in the system, this tells you the energy of that electron as you move the bond. Okay, so this is a potential energy, right? It's the potential energy of the electron as a function of the distance between the two atoms. At long distance, there's no potential because the atoms aren't interacting. At short distance, there's a ton of positive potential, repulsive potential, because the interaction pushes them apart. And there's a Goldilocks where they're attracted. So this is a potential energy. And we have a special name for this kind of curve. All right, so you can call this the potential energy of the electrons, which is a function of R. And these surfaces, these potential energies are called potential energy surfaces, all right, or PES. If I can measure the PES for my system along all the different bonds, all the different coordinates of my system, I know the molecule's electronic behavior exactly. Because what can I do with this potential? I can put an electron or I can put a bond in here and think about the motion of the bond as a function of its displacement. I have a potential energy of that bond. And so I can solve the Schrodinger equation. So what I can do is take this in and plug it back into my Schrodinger equation. Plug this into H psi is equal to E psi. Right? And what I should get out of this are energy levels that look like this, right? We should get energy levels out of this because we now have a potential, right, that correspond to different excitations of the bond. Just like we have in a particle in a box. What we've done here now is instead of having an electron in a box, we have two nuclei that are moving, and we're allowing the electrons to relax between them. So the nuclei define the box, and we're calculating the energy of the system between those two limits. Of course, the electrons can be outside of those atoms as well. This is an infinite potential. But you can see that the potential is defined by the presence of those two protons. And if the interaction is 0, very far distance, and then when it's really close, it's very positive. But in some sense, the electron can be anywhere around this proton. But what this is telling us is that there are, right, this is just a potential, just like our box gives us, but it's not a defined potential and it changes as a function of the position. But still, we have a potential energy surface and it has this deep bound, attractive region in it. We would expect that there might be energy levels. And what we're going to find next week is that, in fact, there are energy levels in there. And so what are these? What do we call these energy levels? What are these motions on this potential? These are called vibrations. So this is molecular vibration. These are the excitations of the bonds. Right, so vibrations come out of the theory of molecular vibrations comes from the Born-Oppenheimer approximation. If we didn't have the Born-Oppenheimer approximation, we'd have to think about how the electrons are moving as the nuclei are moving. What we have here is that we're moving the nuclei, and at each point, we're waiting for the electrons to rapidly relax. But if they were both moving at the same scale, it would look way, way worse, right? Because it couldn't have one dimension. It would be dependent on all the coordinates. And so this potential now defines our vibrations, and this is how we get vibrational spectroscopy. Right? Vibrational spectroscopy assumes that the nuclei are much more slowly moving than the electrons. All right, so that's going to be our first goal starting next week, is to start thinking about vibrations. Motion on this potential that's created from the presence of two nuclei at some distance. Kind of a dynamic box that's changing. There's some electrons shared between them. Right? What do I got? Right. I'm actually going to finish a little early today. I just want to kind of close up shop. So let's think now, let's go back to tally up the different motions that we have. So let's finally finish up what we're talking about here and categorize all motion together. All right, let's define a very generic molecule. I don't want to be specific. A 3D N-atom molecule. Okay. I don't want to make it a linear molecule. I want it to be three-dimensional. Maybe it could be ethane. Ethane's a perfectly fine, ethanol is a perfectly fine one. I don't care what molecule it is. I'll just draw ethanol. Okay. How many different coordinates does this atom, in the Born-Oppenheimer approximation, how many different coordinates does this system have? How many different ways can we move the nucleus? So the question I want to ask is, how many nuclear coordinates do I need? Well, let's just take an atom and we think about the position of the oxygen, right, where it is relative to some axis. Right, I got X, Y, and Z here. Right. The position of the oxygen, so I want to go RO. I'll draw a little vector. Right, it has three coordinates. It's a vector with the X coordinate, the Y coordinate, and the Z coordinate. Right, so you need three coordinates to define the position of an atom. There are N atoms, so that must mean there's three N coordinates. But let's think a little bit about these coordinates. All right, let's say we want to look at motion and how the molecule is moving along these coordinates. Well, we can choose a set of coordinates such that all the atoms move in the same direction, in the same displacement. So let me just kind of draw that, right? One way we can move is all atoms move at the same, atoms displace the same. All right, so I'm just going to draw HCl just not to be lazy. right? Where we take the CL with this vector, we move in this direction, and then we have the same vector where the R is moving, or the H is moving in the same direction, right? Right, so there are 3 different ways to do this, right? We can displace along X, we can displace along Y, and we can displace along Z, right? This is translation. Right, so 3 of the coordinates, 3 of the different ways we can move all the atoms are just translation. So 3 translation coordinates. All right, what about this one? There's another type of motion that we can do. And I'm going to go to a different molecule. One of my favorites. CO-nitrile. There's another way what we can move the coordinates around. We can adjust all of the atoms in such a way. Kind of draw it like this. You'll see what I'm doing in a second. Where I move them all in some direction. And all I do now is I flip it 180 degrees. The center of mass of the molecule has not changed. If I put a point here and call this R0, R0 is still in the same spot. It hasn't moved. So there's no translation, but the molecule has changed. No translation of center of mass. Right, there's our center of mass in the middle there. But the molecule is clearly moved. Right? We've rotated it. So there's also rotation. And there are 3 degrees of rotational freedom. 3 rotations. Rotational coordinates. We'll come back to that later. Right? So of those 3 in coordinates, there are 3 of them that are just due to translation, 3 different types of ways to move the atoms of translation. There's 3 that are rotation. What's left? Well, the ones that are left are where we're now displacing all of the atoms relative to each other. Where now the distances between the atoms are no longer conserved. Now we're stretching things. Right, so the other type of motion, I'll draw it like this. Right, let's put the center of mass on a molecule right here. Here's the center of mass. Right, is where the atoms displace relative to the center of mass, but the center of mass doesn't move. So maybe I move this atom this way a little bit, this one this way, and this thing this way. And that gives me a stretched out molecule. Right, stretch out molecule, but the R0, the center of mass, hasn't changed. Same place. Okay. So these are now atomic displacements relative to the center of mass. These are vibrations. And how many are left? Well, there are 6 we've already accounted for, so there are 3n minus 6 vibrations. Okay. 3 types of motion. We've missed 1. These are all nuclear. Right? These are just motions of the nuclei. We haven't considered the electron. But we know electrons can get excited. Solid in particle in a box. We can excite an electron. And there's also electronic motion, which is much more complicated. And so the Born-Oppenheimer creates a hierarchy of motion. Right? There's 4 different types of motion. There's translational. There's rotational. There's vibrational. And there's electronic. And these turn out to be at different energies as well. And they go up in energy. Translational, it tends to be that we don't really even think about translation. Translation is basically a continuous process. The energy levels are so small space. That's what you're going to calculate in the homework. So this doesn't, we don't really do any spectroscopy. This is basically no energy required. Heat, the thermal energy of the universe heats it up, right? That's all you need. Rotational requires microwaves. Vibrational requires infrared. And electronic is ultraviolet and visible. Right? And in terms of energy scale, we can say that this is on the order of about a thousandth of a wave number. This is about a wave number in energy. This is about 1,000 wave numbers in energy. And these tend to be about 100,000 wave numbers in energy. Okay. So the system, Born-Oppenheimer approximation, gives us this hierarchy, this Jacob's ladder of motion that are all well separated by energy. Right? This is why we do different spectroscopies and we get different information, is because the hierarchy of motion of electrons and protons, nuclei, spread things out. And it allows us to focus our spectroscopy, right? Translational, I wouldn't really call that spectroscopy. This is literally what happens when you heat a sample up, right? You're exciting velocities, translation, right? So that's just heating. I should just say this is heating. I'm just going to write that. This is your oven. Let's just say heat. You don't need a lot of energy to excite translation, right? You can do it with your breath. Rotational requires about a wave number of energy, vibration 10,000, and electronic about 100. Right? So these give us these really nice regions of energy where nothing else happens in terms of motion. So we can be confident that when we put in vibrational energy, we put in infrared, that we're just looking at vibration. And with rotation, we're mostly guaranteed to be looking at rotations. So that's really, really powerful. That's the whole reason why spectroscopy works and why it's ever useful, is because of this mass difference between the electron and the proton. One thing I want to say, one last thing I want to say, is that what I've described is how the types of motion in higher energy don't affect the lower ones. So rotation, you don't really have to think about vibration much, and with vibration, you don't have to think about electron. That should make sense because you don't have enough energy. What about the other way? Rotation, you don't really have, translation we should just ignore for now, though it's important. But what we find, and you'll see this in rotation 3, is that when you go the other way, they start to depend. The vibrational spectrum depends on the rotations. And the electronic spectrum depends on the vibrations, which depends on the rotation. And so when we do the third rotation, we're going to do spectra at these two different levels. I wish we could do a rotational one, but the instrument's not ready yet. When we do an electronic spectrum in rotation 3, you're going to see that the spectrum is complicated by vibrations. The molecule is changing along with its electrons, also changing vibration. So both of these things happen. And then when you do the vibrational study of sulfur dioxide, SO2, in the third rotation, you'll see that their spectra is complicated by rotation, right? You go down one ladder. If you have enough resolution, you can see even more. Iodine, we'll do this electronic spectra of iodine. If you had a good enough laser, you could see vibrational and rotational structure and splitting spectrum. You can see the effects of all the lower energy motions. So the system gets complicated downwards, but not upwards. So that's why we choose to do things at low energy often, because they simplify things. Right? NMR is another thing. I could probably put it right here. NMR kind of sits right there. Which is a very different, this uses radio, which is about 0.01 wave numbers. Right? So there's NMR as well. Right? But NMR doesn't really care about rotations for the most part. NMR doesn't care about vibration, electronic. NMR doesn't affect these two, any of these. That's not true. You can see NMR results in electronic. Actually, you definitely can't tell them apart now that I think about it. So the idea is that complication goes downwards. The higher energy you get, the more complicated the spectra get, because you can now excite vibration and rotational motion. Because you're now at 100,000 wave numbers, it's easy to do something at 1,000 wave numbers. But when you're at 1,000 wave numbers, it's impossible to do something at 100,000. So spectra gets simpler in this direction and get more complicated. Sorry. Spectra gets simpler in this direction, more complicated in this direction. So it's a one-way ladder. It's a one-way ladder. That's Born-Oppenheimer. Very, very important. Central to chemistry and woefully underappreciated. Okay, so this is where we're at. This is where our goals are for the rest of the semester. We've already done translational motion. That's a part of class. We're done. So what we have to do now is look at the rest of it. Right? So what we're going to start on Monday or Tuesday is vibrational. Right? That's a really good place to start, even though it's kind of in the middle. Well, then we'll transition into rotational because the physics of rotation is very useful for electrons. And then what we're going to do is cap off our theory by tackling electronic theory by first looking at hydrogen and then helium, and then starting putting atoms together to make molecules. Okay, so that's our goal for the rest of the semester. Have a lovely weekend.
No, I didn't think it. Yeah. I went on some of that early. Why